Thank you everyone for coming today. My name is Ahmed Karam. I'm a machine learning developer from GDG Jeddah. And GDG Jeddah is a community supported by Google to spread the technical knowledge across the community. You can join us from Meetup or you can follow us in Twitter. The topic of today is low latency Kafka Neo4j data streaming on Google Cloud. Our speaker is Matt. Matt is the founder of the Kettle project since 2001. He is working as a chief architect of solutions Neo4j using Kettle to load data into graphs. Welcome, Matt, and thank you for your speaking.
Thank you very much for that wonderful introduction. Like I said, yeah, low latency Kafka to Neo4j data streaming. Let's take a look at this lightning talk agenda. So I'm going to go over what we're doing today, how we're doing it, and see how we can influence the latency in the pipeline, and then we're going to calculate some real life deltas. So what we're doing today is we're running a simple data pipeline, and we're going to simulate an app that writes messages to Kafka, and we're going to read them back, parse them, look up some extra data, and write them to a Neo4j graph, right? We're going to have a fake topic of the day, Pokemon. So our app is storing basically, fake detections of Pokemons. People find Pokemons in a certain location at a given time, right? And we want to see how fast or slow data ends up in Neo4j, and we want to measure then the overall time it took from the app um, to the Neo4j server. Right? And then we can do all sorts of cool things with it on the Neo4j side, but that's a topic for another day. And we're trying to not measure the performance, the throughput of the Kafka and Neo4j server, just latency for now, right? Now, as a first warning, fast, slow, low, or high, that those are all relative things. And in fact, in today's setup, I went out of my way to make things slow as possible to make it kind of interesting, obviously. And so how are we doing this? So we're using Apache Hop. It's the Hop orchestration platform. You can visit at projecthop.org. So if you see a fancy GUI float around or something, feel free to give it a try and join our community. That's the point of us doing an Apache incubator cycle. And Hop supports Apache Beam. This is another cool Apache top level project. Beam is a shortcut for batch and stream, and it supports a common application programming interface for data processing agents. And it supports a whole bunch of engines. Specifically for streaming, there's a couple of interesting ones. Apache Flink for stateful computations. It's very good, actually. You should give it a try if you haven't heard of it. Apache Spark, a lot of people know it, analytics engine. And obviously also Google Cloud Platform Dataflow, which is the engine I'll be using today. It's kind of was kind of in the title of the talk. So that one is a fully managed service for executing Beam pipelines. It instantiates its own engine on the Google Kubernetes cloud. So that's very convenient. So the first pipeline I want you to look at with you is how are we going to generate synthetic data? Uh, we want to have some kind of never-ending pipeline that generates fake user IDs and fake Pokemon topic data. So let's switch over to Hop and take a look at this. As you can see, this is like, yeah, you have a lot of data orchestration tools out there that have similar things. This says, okay, I want to generate a fake message every second. This is not meant to produce like a gazillion rows or test the batching performance of whatever pipeline. This is just calculating latency. This generates random UID for our Kafka message, calculates a user ID from 0 to 10,000, 9,999. And this is a transform that generates fake Pokemon data. So let's take a look at what comes out of here. So the Pokemon name and the Pokemon location, a UID, some timestamps, and then we create JSON out of this, a message, and this is sent to a very slow Kafka server here that I set up on my test server. So these JSON messages are basically what gets sent over the wire. And then after this, what we're going to do is we're going to read that data from Kafka, parse the JSON back out, and look up the information in a Pokemon dictionary. So if you want to know more about the Pokemon itself, we can do that there. And we're going to write to Neo4j. So I'll switch back to the Pokemon data processor. So this is a Kafka consume transform. This uses the Kafka YO connector from Apache Beam. It adds a system date just to see what given time a piece of information, a detection actually parses through the pipeline, parse the JSON, look up Pokemon details using a data set. You know, it has all sorts of information about the Pokemon, which type, fire, water, legendary or not. You know, I'm not a Pokemon expert. You could do all sorts of other things in this pipeline, like look up information um, anywhere, you know, any kind of web service, any kind of other data source. You could combine Beam and non-Beam data sources. And then we're going to write them out to a Neo4j um, instance, a very slow one again, just to see what the baseline is for the latency. And we're going to use an unwind statement to yeah, to patch those things up. And we're also going to add like a transaction date time to see at which given time Neo4j accepts the data actually, not the first row of, let's say, a set of records, but the transaction date, the whole thing. When is it actually in the database? And so in this case, what we're doing is we're not using a standard local pipeline configuration, but we're using Dataflow, and we're running this on a small standard instance on the East Coast, and our Kafka server is over here in Europe, in Germany, actually. And so what we're trying to do is, okay, how long does all this take? We can take a look at this pipeline in a different way, right? So when you run this pipeline in Google Cloud Dataflow, it looks like this. It's basically the same components that we saw in the Hop pipeline, but now visualized in a different way. So and like you see, it adheres to the 1 element per second throughput. And these metrics that we're generating, they're the ones that you see here in the Hop interface. So it's nicely reflected. So now let's go back to the presentation for a second. Okay, so what are the things that influence this pipeline? So Kafka is a big, actually a big part of because Kafka batches things up. You know, even in a streaming pipeline, um, you need to stop it from waiting too long. You need to specifically set things like fetch max wait in milliseconds or the max pull records. And there's like a whole bunch of parameters that you can set in Kafka, and they all have an influence. Things by default, there's like a thousand records or something, and maybe that's a good number if you have millions of records passing through Kafka at any given time. You know, batching them up in a large group might be perfectly fine, but if you work with smaller sets of records, then you might want to reduce that tremendously, just to force the records to be pushed through a pipeline, a streaming pipeline. It doesn't really matter what kind of technology you use. This is specifically for Kafka, right? So play around with the parameters, and you can test the same pipeline without any other components, without any lookups or Neo4j involved, and see what kind of throughput you get there. The Apache Beam pipeline also um, doesn't really stream the data record by record, but uses bundles of data, and it keeps track of the bundles of data as they pass through the pipeline, just to make sure that if any node in a parallel world, you have multiple servers, multiple nodes running, if any of those bundles fails to process correctly, that you can restart that processing capability. And so if you have larger bundle size, you can have a higher latency, right? I left a link here if you want to know more about the runtime model of Apache Beam. Underneath, Flink, Spark, and Dataflow also use slightly different variations. Flink, for example, allows you to fine tune the bundle sizes and everything to really tweak those for your own needs. Then obviously Neo4j likes to get data in batches as well, so that one also has has an influence on the performance. So if you have lots of data coming in, you might want to make the transactions, you know, the records that you send through the unwind statement that I showed you earlier a little bit larger, right? However, large transactions increase the throughput. They also increase the latency. So there's that in mind. Um, so batching in a massive parallel pipeline is complicated. So you have all these three big ticket items that I showed you. Uh, and so what we did in Hop is we help you by flushing the bundles. So we have added two extra options: the transforms flush interval and the transforms buffer size. What that means is that, okay, so you have a bundle, let's say 5,000 records in it. We want to have the ability to say, well, after half a second, I want you to commit some things already to Neo4j so that we don't have to wait until we have 5,000 records. At one record a second, that's going to take too long, right? The same for the buffer size. You know, I want to do a flush and commit every couple of records or every 500 records or whatever. And so this flushes these bundles and puts them through. Just to go back to that data flow, these are the options that I mentioned. This is set to half a second and a very small buffer size because we're dealing with small amounts of data. Let's take a look at how we're going to calculate the deltas because, you know, unless we measure the times, the deltas, with delta I mean uh, the time from a Pokemon detection to the time that we actually store something in Neo4j, or the time that we read something from Kafka with that system data timestamp we stored in Neo4j. Without those things, we actually don't know what's going on, right? We could be very fast, and then occasionally we might slip up. So we keep and store these timestamps in Neo4j, and then we read the timestamps back out. We calculate averages, the minimum, the maximum, and the 90th percentile. So let's take a quick look at how we do that. All right, let's go back to our simple transformation, our simple transform for Cypher. And basically what we're doing here is saying, okay, give me a list of all the detections, um, return the Neo4j date. And we can also take a look quickly, just to look at the data model. Let's take return D limit 10 maybe. All right, so these are detections that are ending up, and we have modeled it like this. So we have a user ID, a Pokemon that was detected, and a town. And in those detections, we have the detection date and a generated key. Neo4j date is when we actually have the transaction committed, and the system date from the Kafka server. And with these 3 days, we can do a simple estimate. Now, if you have other expensive operations in your pipeline that you suspect might take a lot of time, there's nothing wrong with taking another couple of snapshots, snapshot dates, and storing them in Neo4j. In general, the principle is that the more we know about the data, the better off we are, and then we can do something about it. So here we convert some data. Let's run this. We're going to run this on a local engine, not on Dataflow. And so here we have the 3 dates. And here's a bit of JavaScript to calculate the deltas. Please make sure that you correct for any kind of time zones that you're dealing with. Because obviously in this configuration, my Neo4j server is running in Germany and Google Cloud Dataflow is running on the East Coast in the US. So that gives you like time zone shenanigans. Okay, so what we have here is we calculate a total latency. For example, here's one 0.132 seconds. Great, right? And the pipeline 0.065 seconds. A very low latency despite the fact that we stacked the deck against us by working across the Atlantic. However, we do see that the time creeps up a little bit, up to half a second maybe here and there. So the best thing you can do there is say, okay, let's run some statistics on this. Let's calculate the average, the minimum, the maximum, and the 90th percentile. Those are like a couple of good things to give you kind of like a feel for what this thing is doing. 0.3 seconds on average, zero point 0.1. However, we see that sometimes this thing can uh, get stuck for 10 seconds, right? Um, so that's a maximum. It doesn't really, it doesn't really affect the average that much, but it is, um, it's worth noting, right? So these exceptions, we can look at these and say, okay, let's take a look at the worst cases, everything over 5 seconds, and then we can say, okay, so this happens every minute or so, always at the same time, and it doesn't really influence the performance of the pipeline. So it's something with my Kafka server, right? Uh, so the bad times, 5 seconds, 6 seconds. So this now can give you certain conclusions to say, hey, I might have to look at my Kafka server. Maybe every minute or so, it's doing a garbage collect. Maybe I need to take a look at this. It's a crappy Kafka server I just set up quite quickly. It's not tuned or anything, so it might make sense. On the other hand, if it's part of the pipeline, then you might say, okay, maybe we need to increase the batch size of Neo4j, tweak some other things, or indeed tweak the parameters of the Kafka consumer. Thank you for taking the time out. You're a wonderful person for doing that, for watching this. Like I said before, please join our Project Hop if you're interested in any of these things. And it's totally free. It's totally cool. And thank you for watching. Appreciate it.